Hello, welcome back to the Honors Pre-Calculus video lecture series for Mr. Billingham's class. This is Honors Pre-Cal 10.5C, the third part of 10.5 Statistical Literacy. And here's what we'll be looking at in this section. In this final section of 10.5, we'll work on how to use randomness. We'll model some simulations, and I'll show you some pretty cool calculator tricks, which will be useful in doing the homework. So, when choosing a sample from a population or assigning subjects to treatments for an experiment, we have seen that attention must be paid to randomness. But how do statisticians achieve randomness? It's actually harder than you might think. Not only are people notoriously bad at mimicking true randomness, we're not even good at recognizing it when we see it. Before the days of computers, researchers relied on random number tables. Entire books filled with pages of digits 0 through 9 generated by cleverly harnessed random processes in natures. Today, we usually rely on computers to generate what are called pseudo-random numbers, which work well for most purposes and which we'll use for this book. So for example 6, a school is asked to choose 10 sixth graders at random to be part of a multi-year educational study. If there are 135 sixth graders at the school, how can they be chosen without bias? So we're going to do this with a calculator. First, using any method at all, assign the numbers 1 to 135 to the sixth graders in any order, alphabetical, etc. Doesn't matter. This isn't where the random piece comes in. Now we need to generate 10 random numbers between 1 and 135. I'm going to do this with my calculator. On your calculator, if you go to Math, Probability 5, you'll see randint. And the way randint works is as follows. When I hit enter on the current screen, it puts me back to the home screen with randint and a left parentheses. I'm going to put in 1, 135, 10, right parenthesis, like this. This command asks the calculator to come up with 10 random numbers between 1 and 135. You can't see the 10, but it's there. You also can't see the numbers, so I find it helpful to do something else instead. I enter the same command as before, randint 1, 135, 10, but now I add store in list 1. And list 1 you can find as second 1. And what this does is it puts all those numbers into list 1. And so if I go to stat edit, I'll see this. And so you'll see 10 random numbers from 1 to 135, and you could just notify those children that you'd assigned those numbers to, and those would be the ones used in the study. Now there is one slight drawback in this. Rand 1, 135, 10 does not guarantee that the number is going to be unique. Just the same way if I roll a die 3 times, I don't know that I'm not going to get 2 6s. So if I got a repetition of a number, I would just repeat this and take the first unique number that I got. I could also just repeatedly call randint 1, 135. Every time I do that, it generates a new pseudo-random number between 1 and 135 as shown in this screen. So instead of getting the original 10, I could have just repeatedly done it until I had 10 unique random numbers 1 through 135 without repetitions. So that's how to handle this problem. In example 7, we want to split 50 people who suffer from a certain medical condition into 2 groups. One of the groups will be given a placebo, and the other will given an exactly similar appearing pill that actually contains a new drug. Half will be treated with the drug, half will be given the placebo, and again, if I want to do this properly, I want to completely randomly assign the people to the 2 groups, and I also don't want the experimenter or the person who's actually administering the doses to know which is which, because he could influence the patients. So here's how I do that. I'm going to go to second stat, which is list, and then ops, and then 5, which is sequence. Should look like this. When I hit enter, I get the following screen. For this fairly simple case, We want the expression to be x. We want the variable to be x, which seems a little odd when you're first getting used to it. We want the variable x expression to start when x is 1 and end when x is 50 and go up by 1. So what this is going to do, it's going to create a sequence of the numbers 1, 2, 3, 4, 5 all the way up to 50. And then when I paste that into my home screen, it looks like this. At this point, I'm just going to add in the familiar store list 1, and don't worry about the fact that we already have some numbers in list 1. This will write right on top of them. And there are 50 of them, so it'll completely cover them. So that's what we'll get. Now I'm going to generate 50 random decimals between 0 and 1 and put them into list 2. Here's how I do that. You'll find the rand command as math probability 1. So at this time, I will have the numbers 1 through 50 in order in list 1, and in list 2, I'll have just random decimals in between 0 and 1. It'll look something like this. So in this picture, you can see at least the first part of the list of 1 through 50, and in the second one, you see all these different 5-digit, actually there are more, you can see each one has many more digits, numbers that are between 0 and 1, and they're stored in list 2. Now I'm going to sort the numbers in list 2 while keeping the number in list 1 that was with it in order. So let's say that the 0.5147 in list 2 that's at the top winds up being the 26th number. Then after it's sorted, 1 will also be the 26th number on the left. And the command to do that is as follows. I want to use the sort A command, and it is located under second stat and then ops and then number 1. When I hit enter, it'll pop out on the screen, and I want to use the following. I want to use sort A L2, L1. And what this does is it tells the calculator to sort both list 2 and list 1, keeping them together like a list of ordered pairs. They have to be the same number in each, but there are 50 in each. And sort them in order by putting list 2 in increasing order and keeping their corresponding elements from list 1 in the same position. So the result's going to look like this. And if you look closely, you'll see that the elements in list 2 are put in perfect order from the lowest to the highest, and the elements that they used to be next to in list 1, they're still next to, but those have been reordered. So now I can go back to the problem. I can take the first, if I took the 50 patients and I gave them each a number 1 through 50, the ones that show up in list 1 in the first 25, so patients 39, 7, 38, 11, 21, etc., they might be assigned to the group that's getting the actual drug, and the last 25 numbers in the list, down at the bottom, they would be getting the placebo. And so that's a perfectly good way to randomize the two lists. So for the next question, how can we use a calculator to simulate probabilities and assess statistical significances? So here's the problem. Let's assume that Fred is a 70% free throw shooter. 70% chance on any particular shot that Fred will make it. He doesn't get tired, he doesn't get better, he doesn't get worse. So how many shots would it typically take him to hit 7 consecutive free throws in a row? So I need somehow to come up with something that corresponds to Fred being a 70% shooter. So what I would use in the calculator is I would enter the following into my calculator. When I do rand 09, every time I hit enter and repeat that calculation, it generates a number from 0 through 9 inclusive. And so what we're going to assume is the following. Anytime the calculator gives us 0 through 6, 7 different outcomes, we'll assume that's a success. He made the free throw. And if we get a 7, 8, or 9, we get a miss. And this is what happens if we keep repeating this over and over and writing down the outcomes we get until there are 7 successes in a row, and it's pretty surprising. The authors were pretty astonished by this themselves. So the very first screen sequence, you can look through it, it's not until that very last group, 4141, 466, they got 7 successes in a row. Until then, over and over and over, they would lose. Like 614, they're all good, then a 9, 126030, and then an 8, and so on. So that's an astonishing number. The calculator version of Fred had to take 70 free throws in a row before he hit 7 successes in a row, which is pretty astonishing. And then amazingly, right after that, the very next 7 shots were all success. The next 7 shots were all successes. And then the next one, we only had to have 2 that were misses before we got 7 in a row. So this is pretty bizarre. You can see, though, if you had a computer do something like this hundreds and hundreds and hundreds of times, you could easily calculate experimentally rather than mathematically how many shots Fred would have to take in a row before he would, on average, get 7 free throws in a row, which is pretty interesting. It gives us a way to sort of confirm what we might do. You might try to think about mathematically how you would calculate how many shots Fred would need to take to get 7 in a row on average, find the expected value of that. But I think that's a pretty difficult question. So earlier in the chapter, in example 7, we talked about randomly assigning 50 subjects to treatments in an experiment designed to test the effectiveness of a new drug. Suppose that at the end of the experiment, 64% of the 25 subjects who took the drug showed improvement, compared to only 40% of the 25 subjects who were given a placebo. Could that difference of 24% arise by random chance? Or is that statistically significant evidence that the drug is indeed effective? Well, I can kind of look at simulations to figure this out. So 64% of the 25 people that took the actual new drug showed improvement. That's 16 people. And 40% of the 25 who took the placebo showed improvement. That's 10. That's a total of 26 out of the 50 that showed improvement. So the idea is we're going to generate 26 ones, meaning showed improvement, and 24 zeros, and this represents the outcomes, and then we're going to randomly split them into 2 groups of 25 by sorting them. And we'll look at the percentage of ones in each group to see how big a difference might occur just by chance. So if we do that, you get the following table. So again, the strategy is we generated a sequence of 26 ones and 24 zeros that corresponds to how many people in the survey showed improvement and how many didn't. And then we randomly sort that and see how many showed improvement in the first group and how many showed improvement in the second group. And you can see, for instance, that in trial 1, 14 in the drug group showed improvement, 12 in the placebo group. And they're listing the differences. And you can see that we can get a 40% gap there. In trial 4, we had, in the drug group, 18 showed improvement and 8 showed improvement in the placebo group. And that would be pretty compelling. But we also have a negative 16%, a 0%. So how could we look at this big time overall? So the authors say that they ran the simulation for 1,000 trials and put the information together in a histogram. In the original experiment, there was a 24% difference between the 60% in the drug group and the 40% in the placebo group that arose, and we wanted to know if that indicated the drug was successful. But as we saw by running this experiment 1,000 times, you can see that those red histogram bars to the right, that is what would happen just through random chance. And that is about 9% of the time. So that sort of says that our result of that 24% isn't that significant. 91 out of 1,000 trials showed more than a 24%. And so we ought to have a little rule for helping us decide when an experiment shows a significant result. So the common rule of thumb is that in order for an observed outcome to be considered statistically significant, there must be less than a 5% chance than it could have occurred randomly. So had the drug group outperformed the placebo group by 32% or more, we'd consider that to be evidence of the drug's effectiveness, but 24% isn't enough. In the simulations, differences that large were quite rare. They only happen about 2.8% of the time. So the decision rule can vary with the gravity of the situation. If we're simply curious to see whether the rate of smoking among middle school girls has changed in the past 20 years, we might accept slightly less unusual results as offering some evidence. An outcome with maybe a 10% chance of occurring might be considered significant. On the other hand, if you're testing rivets that hold highway bridge girders in place, you might want to make it test results that could occur by chance only 1 in 1,000 or maybe 1 in 10,000 to be compelling evidence that they're strong enough. So depending on the importance of the result, you might want to sort of look for really, really strong, compelling evidence. I hope this video lecture has been helpful. It is the last one for this chapter, and I hope you're all staying well, and bye-bye.